All right, 2.1, day 2. Hopefully this will work a little bit better than the first video. So we studied that the derivative of a function is defined by the limit definition, x plus delta x minus the original all over delta x. Then we looked at the equation of a tangent line, y minus y1 equals m times x minus x1. And we said the slope of the tangent line is the value of the derivative at whatever the x coordinate is. But we had to go through the whole limit definition in order to plug in the x value of the point of tangent c. So what we're going to look at today is finding the derivative of a function at a specific value of c. So the derivative at c, all right, so when you know the value for which you want to find the derivative, this is what your book refers to as the alternate form of the definition of derivative. So the limit as x approaches c, original function minus value of the function at the given point c divided by x minus c. So again, if you know the point of tangent c, we can find the slope directly. So here's my function, find g prime of 5. So g prime of 5, using the alternate definition, limit as x approaches 5. Now the two pieces of information I need are the function, which is 2 over x, and I need the value of the function at 5. Now I'm using f, doesn't matter what letter we use. So g of 5 is 2/5. So limit f of x minus f of c, all divided by x minus c. Alright, so we have two fractions in the numerator, getting my common denominator, 10 minus 2x divided by 5x. And then I'm going to, I know that's really over 1, so get rid of the fraction within a fraction. Limit as x approaches 5. Notice we can factor out a 2 from the numerator. Do not expand the denominator. These are opposites of each other, so they cancel to -1. Limit as x approaches 5, -2 all over 5x. Now when we make the direct substitution, this gives me the value of the derivative when x is equal to 5. So now if I ask you to write the equation of the tangent line, y minus y1, the y value at x is equal to 5, we determined to be 2/5. The slope of the tangent line, -2 over 25, x minus the x coordinate of the tangent line. Okay, so given this function, find the derivative at -1. F prime of -1, limit as x approaches -1. The alternate definition, the function minus, well, what's f of -1? Plugging -1 into the function, I get -1 plus 1, so I get 0, all over x minus c. So limit as x approaches -1, x cubed plus 1, all over x plus 1. Now direct substitution would give me 0 over 0, so what can I do algebraically? Factor the numerator, x plus 1, x squared minus x plus 1, all divided by x plus 1. These cancel each other out. Limit as x approaches -1, x squared minus x plus 1. Now when I make the direct substitution, -1 squared is 1, opposite of -1 is +1, so 3. F prime of -1 equals 3. So what does this mean in words? The slope of the line tangent to the function is 3 at the point -1 comma 0. I left some space for the problems. All right, take a minute, pause the slide so that you can copy down the notes. If a function is differentiable at x is equal to c, then the function is continuous at x is equal to c. So your book refers to this as differentiability implies continuity. So what does differentiable mean? A function has a derivative, so f prime of c exists. All right, so if the derivative exists at c, then a function is continuous at c. So we're going to look at cases that discuss the converse, which says if a function is continuous at a given number, is the function differentiable at that value? So continuity, where did continuity come from? The domain of the function. Okay, so if a function is continuous, does it mean that f prime of c exists? That's what we're going to look at with the next examples. Find the derivative at 0 if my function is the absolute value of x. Okay, so we're finding the derivative at a specific point. So I can use my alternate definition, limit as x approaches 0, function minus value of the function at 0, all over x minus 0. I get my limit as x approaches 0, absolute value of x over x. Okay, hopefully this is ringing bells, okay, but this limit does not exist. Why does it not exist? We studied this several times. We looked at it often last chapter. Direct substitution gives us 0 over 0. So if we look at the one-sided limits of this function, if x is positive, the absolute value of x is just equal to x. The absolute value doesn't do anything to a positive number. So the limit as x approaches 0 from the right is positive 1. The limit as x approaches 0 from the left-hand side, though, what does the absolute value of x do? It takes the opposite of the number that's inside. If the one-sided limits are not equal, what can we conclude? The limit as x approaches 0 does not exist. Okay, so let's think about our theorem. We're looking at the question, if a function is continuous at a given value of x, is the function differentiable? Domain of the absolute value function is all real numbers, so that includes 0, but we just showed that the derivative at 0 does not exist. Okay, so going backwards, we just showed a counterexample, so automatically the converse of that theorem is false. If a function is continuous, it does not mean the function has to be differentiable at the given value. All right, let's look at another case. Okay, so let's find the derivative of 0 for the function f of x equals x to the 1/3. This is the cube root function. The domain of the cube root function is also all real numbers. So let's look at our alternate definition. Limit as x approaches 0. The function is x to the 1/3 minus the value of the function at 0 is 0, all over x minus 0. So I get the limit as x approaches 0, x to the 1/3 over x. Dividing like bases, we subtract exponents. So negative 2/3. This becomes the limit as x approaches 0 of 1 over x to the 2/3. When we attempt a direct substitution, what do we get? We get number over 0. What does that tell us about the limit? The limit does not exist. So again, we just showed another counterexample. Function is continuous on all reals, so the function's continuous at 0, but the value of the derivative does not exist at 0. And we'll sum up what all of these examples represent. All right, let's look at this one. Find the value of the derivative at 2 if the function is square root of x minus 2. So the domain, we know what's underneath the radical has to be greater than or equal to 0. X has to be greater than or equal to 2. So this function, 2, is in the domain of the function. F prime of 2, using our alternate definition, limit as x approaches c, original function, minus the value of the function at 2, which would be 0, all over x minus 2. So limit as x approaches 2. Now we can use the same technique here. You don't have to rationalize, although you could, but we have like bases. X minus 2 to the 1/2 power divided by x minus 2. Dividing like bases, subtract my exponents. So 1/2 minus 1 gives me a negative 1/2. So this becomes the limit as x approaches 2 of 1 over the square root of x minus 2. Again, direct substitution gives us number over 0, so this limit does not exist. Alright, and the last one we'll look at today. So, f of x equals 1 over x plus 1. What's the domain of this function? X cannot equal negative 1. If negative 1 is not in the domain of the function, then f prime of negative 1 will not exist at all. Okay? So, domain restrictions, we wouldn't be able to find the derivative at a domain restriction. Alright, so again, your homework tonight was from, what was it, page, and this is on Edmodo, page 104, numbers 25 part A, 27 part A, 31 part A, and then numbers 39 to 42. And I posted it on Edmodo. I don't know if it'll make sense looking at it in that form. But for number 27, use the expansion of a plus b cubed, 1a cubed, plus 3a squared b, plus 3ab squared, plus 1b cubed. Use that expansion for number 27. I'll see you tomorrow.